Dear students, welcome back to our channel. Today we'll discuss two more theorems in the chapter Eigenvalues and Eigenvectors. In the last class we have seen two theorems. Now we will see theorem number 3. The characteristic roots of an unitary matrix or of unit modulus. Very important bit this is also. Now we'll see the proof. The characteristic roots of a unitary matrix or of unit modulus. Suppose A is an unitary matrix. Therefore, by definition of unitary matrix, A power theta into A equal to I. We take this as 1. Now we have to find the characteristic roots of this unitary matrix. Let us consider lambda is a characteristic root of this unitary matrix. Therefore, Ax is equal to lambda x, where x is a characteristic vector of A corresponding to lambda. Therefore, A into x is equal to lambda into x. We take this as equation 2. Now we take conjugate transpose on both sides. Conjugate transpose on both sides of equation 2. Ax whole power theta is equal to lambda x whole power theta. Now we write this in reverse order. X power theta into A power theta is equal to, since lambda is a scalar, no need of finding transpose, just we find out conjugate. We write it as lambda bar x power theta. Now we consider this as equation 3. We multiply equation 3 and equation 1. Equation 3 into equation 2 implies this into this, LHS into LHS, x power theta into A power theta into Ax is equal to RHS into RHS, lambda bar x power theta into lambda x. Now we rearrange them. X power theta, we write these two in one bracket. A power theta into A into x is equal to, since lambda and lambda bar both are scalars, we will bring them out, and into x power theta into x. Since A is a unitary matrix, by definition A power theta into A is equal to I. Now we replace A power theta into A, I, x power theta into x from equation 1. This is equal to lambda bar into x power theta into x. By identity law, I into x is equal to x. I into x is equal to x. This is equal to lambda bar x power theta into x. Now we take x power theta into x as common. We bring this to the left side and we take this as common. 1 minus lambda bar equal to null matrix. Since x is a non-zero vector, x power theta into x is not equal to non-null matrix. So therefore, 1 minus lambda bar itself equal to 0. Lambda bar is equal to 1. We write lambda bar as lambda mod lambda whole square. This implies mod lambda is also equal to 1. Therefore, lambda is a characteristic root. Therefore, the characteristic roots of unitary matrix are of a unit modulus. Therefore, characteristic roots of unitary matrix are of unit. Unit means 1. Unit modulus. That means modulus of lambda gives 1. So like that we can prove this theorem. But in competitive exams wise, the bit is very important. The characteristic roots of unitary matrix are always or of unit modulus. Very important bit. Just now we have learned the characteristic roots of unitary matrix or of unit modulus. Now we'll see the corollary. The characteristic roots of an orthogonal matrix are also of unit modulus, because if all the elements in the unitary matrix are real, here important note is, if all the elements in unitary matrix are real, then that matrix is called orthogonal matrix. That is why the characteristic roots of orthogonal matrix are also of unit modulus. This is also very important bit. Now we'll see one more corollary. The characteristic roots of a real symmetric matrix are also real. In the last class we have seen the characteristic roots of Hermitian matrix are real. Here one important point is, if all the elements in Hermitian matrix, if all the elements in the Hermitian matrix are real, then that matrix is called real symmetric matrix. That is why the characteristic roots of real symmetric matrix are also real. The characteristic roots of Hermitian matrix are real. If all the elements in that Hermitian matrix are all real, then the characteristic roots of real symmetric matrix are also real. Now we'll see one problem. Show that the matrices A and A transpose have the same eigenvalues. A and A transpose have the same eigenvalues. Now we'll see the proof. We have A minus lambda I whole transpose is equal to A transpose minus lambda I transpose. Since lambda is a scalar, we need not find a transpose. We find a transpose only for the matrix. So that is why we are neglecting here. Now this is equal to A transpose minus lambda I transpose is I. Because on interchanging the rows and columns in the identity matrix, again it gives identity matrix. Therefore, A minus lambda I whole transpose is equal to A transpose minus lambda I. We got this. Now we take determinant on both sides. Det A minus lambda I whole transpose is equal to det A transpose minus lambda I. In the determinants, we know this property. Det A transpose is equal to det A. Det A transpose equal to det A. So we apply this formula here. Det A minus lambda I whole transpose is equal to A minus lambda I det. So just we are removing this transpose by using this property. Therefore, det A minus lambda I equal to 0 if and only if det A transpose minus lambda I is equal to 0. This is equal to 0 if and only if this is equal to 0. This implies lambda is an eigenvalue of A. Lambda is an eigenvalue of A if and only if lambda is an eigenvalue of A transpose. So we observed both A transpose and A has same eigenvalue. Therefore, A and A transpose have same eigenvalues. Characteristic roots are same for both these two matrices A and A transpose. Now we'll see one more important bit. Show that 0 is the characteristic root of matrix A. Suppose we call this matrix as A, which implies matrix A is singular. 0 is the, first we take 0 is the characteristic root of matrix A. This by implies lambda equal to 0, characteristic root lambda equal to 0 satisfies the equation, characteristic equation that A minus lambda I is equal to 0. This by implies put lambda equal to 0, that A is equal to 0, which implies A is singular. Therefore, 0 is the characteristic root of matrix A if and only if matrix A is singular. These are very important bits in this chapter, eigenvalues and eigenvectors. Hope you understood this class. Thank you.